Julia Plavnik. I'm a mathematician, so I'm part of Indiana University at Bloomington. And I'm a mathematician, and I'm also in the Quantum Center at IU. And I'm very happy to thank the funding from NSF and from the Simons Foundation. I have an NSF career grant to study some algebraic objects that are key for topological quantum computation, and that's some of what I will tell you today. And I'm in a collaboration with physicists and other mathematicians studying categorical symmetries, global categorical symmetries with the Simon Foundation. So I'm from Argentina. If at some point you don't understand what I'm saying, please stop me. I'm happy to repeat. And also, if you have any questions, please let me know. The idea of the slides that I prepare are an intro to the kind of mathematical questions that we are thinking with respect to topological quantum computing. So maybe let me get started. Just to be all on the same page, I wanted to tell you what I think of when I think on quantum computation. So I'm following this definition from 2003 of Mike Friedman, Alexei Kitaev, Michael Larsen, who is also at IU, Shenhan Wang, who is one of my collaborators and now at Microsoft, but he was also at IU some time ago. And the idea is that quantum computation is any computational model that has the theoretical ability to manufacture, manipulate, or measure quantum states. So that's the idea that we will, or that I will be having in mind. And just to give you some idea on how we think on these things, I wanted to present this kind of a scheme of quantum computation. So the idea is that we have in mind, the principles that we have in mind when we think on this are just the principles of quantum mechanics, basically on a closed quantum system. So we keep in mind superposition, unitarity for the evolution of the operators on time, entanglement, and measurement. So the prototype is the following. We start with a classical function, so things that takes zeros or one. Here we'll have n tuples of 0 and 1s and give you back another thing of the same type, another element that has n zeros or 1s. And what's the goal? The goal is to find f at certain n. And what we want to do is we want to encode this classical information at n in a quantum state. So the idea is that what we want to find is an algorithm. We want to process this state, and this algorithm will depend on f, right? So to go from n to something depending on f. And what we want is, as I was saying, the goal is to measure basically f at n, or to find f at n. So the thing that we want to measure is the state f at n here. And that will appear with certain probability. And the idea is that we would like this probability to be high, to be big, so we can find it maybe bigger than 1/2 or something like this. So the idea behind this, what we are trying to do is we are trying to squeeze classical information out of the quantum state. That's the main idea, and that's the idea of the definition I presented before. So let me tell you one common, or one, and maybe before that, one example of this could be thinking of the Shor's algorithm for integer factorization. So when we want to find the smallest prime factor of certain n, that could be our f at n, for example. So one way to do these kind of things is to think on this quantum circuit model, and we will start with V, 2 copies of the complex. And now what we do is we have n qubits. So instead, you see I'm changing 0, 1 by these now all possibilities of complex or complex squares, and now I'm taking n copies again of this. And now what we will do is we will consider certain matrices, certain unitary matrices that are these, the idea of these time evolution operators. And these are our quantum gate set. I picked 3 of them. In my mind, I was picking the C0, the Haderman gate, and the phase shift gate, but you could think of other number. It doesn't need to be 3. I was having this in mind to say the last part of the result. But the idea is that when you think of a quantum gate set, you have certain finite number of unitary matrices. And what you do is get the set of all the quantum circuits, and what will be quantum circuits for us will be things that you can create using your quantum gates. How we create this, imagine that I want to act on these n copies of B. So I need to have something that can take values in all of these things. So what I will do is I will take these matrices and I will act locally with these matrices. This matrix is the one that I was having in mind, have size 4 by 4, 2 by 2, and 2 by 2, but this could have other forms. And what I do is I act in certain part of this B tensor n with my matrix, with one of these quantum gates, and in the others I act as the identity. So I do nothing in the other spaces. And then I take products of these things, not only one. This will be our quantum circuits. And what happens is that in this way, this gate is universal. So we have this nice result about, or this, basically this gate being universal is that you can get to any other gate by certain finite number of operations or finite number of these quantum circuits. And maybe you cannot get exactly, but you can approximate to any gate sufficiently good. And there is this there is a result about this that it's also nice. Maybe let me see if I want to say something else. So one comment about this quantum circuit model is that this is a quite common model. For example, this short algorithm involves this. And why we don't stop there? Why, if we now have universal gates, we know examples, and we know that it's a common model, why we don't stop there? We don't stop there because there are some problems. It has a big con, that something that it's hard, it's the coherence. So there are some interactions with the environment, and this interaction caused to the model to have some local errors. So for example, you could have bit flips, or you could have phase shifts, or things like this. And there are some solutions, some classical solutions, for example, redundancy, but this is expensive. So error correction is usually expensive in this case. So people were thinking of options to solve this problem, and one possible answer is thinking about topology. So topology is one area of math, and the idea that we will use this area of math is to encode the information more globally. And what will be the advantage of this idea is that when you have small perturbations, small local perturbations, that will not affect your procedure. So I have to say that I'm an algebraist, but I'm very, very interested in topology, and I do study some topological problems. And what I will present as the solution, as this model for topological quantum computation, basically is these two sides of the coin that are topological and algebraic ideas. So let me tell you a little bit about the ABC of topological quantum computation. And here I should have written topological. So there are three basic notions around this topological quantum computation. The anyons, which is more like in the physics side, it's this idea of certain quasi-particles that you will have. The idea of braids, and this is more topological maybe, and the idea of categories, and this is more on the algebraic side. So how are these connected? The trajectory of this quasi-particle or these anyons, so you have these anyons and they will evolve in time, can be described as certain functions in your category. Maybe you have never heard about categories before. Categories are a nice way that mathematicians found to organize information. So we know things about different topics, and what we do is we put the things in certain bags and we compare them using functions. So the idea is, for example, maybe we don't want to study only vector spaces like one by one. We want to study all the vector spaces. So what we do is we study the category of vector spaces and the functions that relate vector spaces. And when I say the functions that relate certain objects, I mean that they preserve the nice property that I'm looking at. In the case of vector spaces is linearity. In that case will be linear transformations. So that are the categories, but these trajectories of anyons are described by functions in very beautiful categories that are called modular categories. And these categories are very special, and I will tell you a little bit more later. But they can also be described, these trajectories of the anions, in a more topological way, that it's using the braid group, which again is a very beautiful algebraic object that has a precise definition, but can be encoded both by equations or by some graphical calculus. And here you can see that these light blue dots that I have are my quasi-particles that are evolving on time. This is the trajectory. And if you see, you could see maybe that it looks like a braid, and actually can be described as an element in this group. So let me tell you a little bit more about these things. What is the computation versus physics side of this story? The idea is that we will start, what we want is to initialize our system. And in the physics side, what we want to do is we want to create anions out of the vacuum. And here, when we do this in the physics side, we will always create them in pairs. It will be the particle and the antiparticle. Then the idea is that we want to do computations. We really want to apply our gates. And these gates can be written in the physics, or can be described in the physics side as this exchange of particles. I'm exchanging the particles, and that it's described by the braids of anions. And the last thing that we want to do is we want to find our output, right, for this procedure. And the idea is that what we do is we fuse our particles, and that gives us a measure. When I say I fuse our particles, like we annihilate the thing that we created before. And what I want to measure is what's the probability that I get the vacuum here again. You see, I started with the vacuum. What is the probability that again I get the vacuum? So that's kind of the computation versus physics model. Now I will go from physics to math. And when I say to math, I will go to the algebraic aspect, that it's these beautiful categories that are my main research focus. But there's another side that it's called topological quantum field theories, and it's on the topology side, and it's very related with these modular categories. It's very beautiful, has beautiful graphical calculus, but I will focus on the algebra. So my anionic system will be, or it's in correspondence with a modular category. The different anions could have different flavors. These anion types are the same as the simple objects, which are the blocks which I use to construct any other thing in my category. To do this, what I'm actually doing is I'm doing a sum of objects. That's how I will see it in the math side. Basically, is that we can, we have this fusion of anions, and the idea here, the fusion of anions, is when I fuse two anions, I don't necessarily get another anion. What I could get is a sum of different anions. And these different things that I will get, the sum of the different things that I will get is a sum of different simple objects. And the same happens with the other operation that I have in the modular category, that it's a tensor product. So I have two operations, addition and product. The vacuum type, the ground state, which I started to, when I was initializing my system, it's the unit for this product here. The antiparticle, I was saying that when we create, we have particle and antiparticle, is something called the dual object. And the annihilation and creation are related with this dual object, because I told you when I create or annihilate, I have these pairs. And these are maps in my category called evaluation and co-evaluation. The particle exchange is the braid for my category, which makes this tensor product commutative. So the order of the factors doesn't matter in this case because I have the braid. And then there are other things. And here I will not go much in detail, but the idea is that I can extract from the anion type observables and the topological spin, I can encode that in two matrices in the side of the modular categories that are called the S and the T matrix. So I will go over kind of fast on these examples, and if you want, we can go back. But the idea is that we like to study these modular categories. And for example, the Fibonacci category is one that I have only two simple objects. The rank is the number of simple objects. So two flavors for my anions, the unit, the one, and one other simple object. This is very nice because the simple object, as you can see, has a funny dimension. It's not an integer number. Actually, this is the golden radio. And the fusion, when I fuse my non-trivial anion with itself, I get the unit plus itself. And if I continue fusing, I get a beautiful sequence that it's called the Fibonacci sequence, and that's why the name is here. And this is my, my matrix. I have another example that now I get with more number of flavors for the anions, more number of simple objects. The dimensions are 1 and square root of 2. The unit always has dimension 1. And here I wrote the fusion rules and I wrote the S matrix. I didn't include the T matrix, but we also have the data. So let me tell you what are the problems that we are thinking. The first problem, that it's the one that we know better, is that we want algebraic models for the things that could be useful for constructed quantum computing, or at least a topological quantum computing, that are these topological phases of matter, which were the topic of the Nobel Prize for Physics in 2016. So it's a topic that it has been studying a lot by physicists. And we are doing this for two-dimensional topological phases of matter, things that you need to think that they live in the plane, not like 3D. And this bosonic, I will not enter in details, but we can talk more later. And the algebraic model are exactly these beautiful modular categories that I was telling you about, actually unitary modular categories. So what we would like to do is we would like to classify these topological phases of matter. We want to know them very well so we know which are useful or not for topological quantum computation. What means classify? It means give you a list. But give you a list depending on something, right? Sometimes I want to know depending on the number of anion types, or depending on the dimensions, or things like this. The goal would be to have something like a periodic table. Like you give me the category and I will give you some numbers or some matrices associated to it, the number of simples, the dimension, the S and T, the fusion rules, or something that tells you everything you want to know about your category. This, it's still, I mean, we are classifying these categories, but still one big question is, what are the things that we would really like to have in our periodic table? Which things are enough to distinguish two different categories? So for example, the two previous categories were different because the number of simples were different. So it's easy for us to take them apart. That's the rank. But having the different rank is enough to take them apart, but not enough if you have two with the same number of simple objects. That doesn't mean that they are the same. So we need more info. That's why I include more info, but this info here, it's not enough to distinguish them. The other thing that we like to do is we like to interpret information theoretic questions. And again, this comes back to this original question of universality, right, of the system. And I will tell you one little thing in a minute. And the other thing that we're trying to do is generalizations. One generalization is going to 3D, right? So here I have a cute picture of this dolphin doing these rings. The idea is that when we think in a plane, we are thinking of our anions to be like point-like particles. So they look like points, if you remember the other pictures that I show you, and that describe these braids. So if now we live in the space in 3 dimensions, instead of looking at points, which will turn to be very boring given some math behind this, we will look at these kind of rings. And when they evolve in time, they will be different. Now they will look like tubes, not like these just braids, so, or strings, right? And there is a theory, and there is a nice group called the loop braid group that generalized the braid group, but we're still studying things like this. And related with this, the interpretation of information theoretic questions, let me tell you that there is a very beautiful conjecture by Professor Eric Rowell from Texas A&M, that he wants to relate one of the values here in our periodic table. He wants to be able to detect universality from one of these values. So the proposal, and here I should have written his name, this is Eric Rowell. The proposal is that it's universal if and only if this dimension of the category is not an integer. In the cases that I showed you before, the Fibonacci category, the dimension, I didn't write it there, but it's not an integer, and that will be universal. But the Ising category has dimension 4, and that category is not universal. So in the known examples, we know that this is true, but we don't know in general. We would like to prove that this conjecture is true. And that will be a big plus because universality is non-trivial to compute, but computing the dimension is something very easy to do. So this will save a lot of time in the labs. And maybe just to end, let me tell you some results that we know. We have worked a lot on this classification program in creating this periodic table. There is work by many people, and here I'm omitting some names. One of the paths is going by rank, number of this anion type, right? And we are not that far in this. We are in rank 6. If we impose more conditions, we know rank 7 and 8. And if we even impose a little bit more with Agustina Chenki, she's a grad student at the University of Oregon, we prove that we can go up to 25 and we know, or 23, up to rank 23, and we know the result, but that's with restrictions. We have also studied the classification depending on the dimension of the category, and there are some results in that direction. These are very like, people keep studying these things. This is a young theory. When I say we have been classifying, this is not that an old theory. We are in the early stages and we need really more examples. So that's one of the things when we're classifying, the things that we find are usually the same kind of things. Most of the examples come from something called quantum groups. And both of the examples that I show you can be realized as quantum group examples. So what we want to do is to construct new categories that are more exotic. So what we try to do is get new things from old ones, so get new constructions. So you give me a modular category or a fusion category and I give you a new one. And there are a classical construction, it's called the Drinfeld Center. And then with my collaborators, we develop a mathematical framework for gauging, which is inspired by physics. And then we develop another thing called zesting, that it's like with the form, we twist a little bit, we add a little bit of flavor to our modular category and we get a new one.